There are times when numbers are required. This is especially true of domestic heating, where major decisions need to be made, such as whether to get a heat pump.
So, what is the one characteristic in a property you're looking for that will make you say, that's the one?
Do you know, you will not be expecting this, and you may find it very geeky, but energy efficiency and sustainability, I take that very seriously.
No, I don't think that at all. It features on most people's wish list these days. I might just have the thing. Fylingdale Court. A development of historically significant property where energy efficiency was the key objective from the outset. They've achieved a heat transfer coefficient of 80 watts per degree Celsius, almost record-breaking.
Oh yes, the heat transfer coefficient. I used to know, but perhaps if you could refresh my memory, that would be very helpful.
Sure. The heat transfer coefficient is the rate at which heat is lost from the building. For each degree, the temperature on the inside is above the temperature on the outside.
Because the heat loss is proportional to the temperature difference?
That's right. It's Newton's law of cooling.
80 watts sounds like a lot. So, if it's freezing outside and I want it to be 20 Celsius inside, so that's 20 by 80 or 1.6 kilowatts. That's almost like having the kettle on all the time.
But what a property. You've got a stunning main room, 5 metres by 5 metres, kitchen with island, separate utility room, 160 square metres in total, and so the heat loss parameter.
The heat loss parameter? So that's different to the heat transfer coefficient?
It's similar, but the heat loss parameter is what people use when they want to know how good the insulation is. So it stays the same whether the property is big or small if it's constructed and insulated in the same way.
Yes, I think I remember. So you divide the heat transfer coefficient by the total area in square metres?
Yes, so with Fylingdale Court, it's 80 divided by 160 or 0.5. It's unprecedented.
But how do they measure the 80 watts? There's a lot riding on this innocent number.
That's a big question.
Hi, my name is Paul Welton. I made this video to show you my ideas on how to measure the 80 watts. This measurement is key to any meaningful discussion about heating, yet currently heat loss calculations make assumptions about the insulation to your property rather than measuring how well it actually works. Is the cavity wall insulation still as good as it was when it was installed 40 years ago?
We really need to have a discussion about EPC. People are going around with the best of intentions, trying to bring up the EPC ratings of the buildings and the U values of the walls by putting impermeable foam-backed plasterboard onto solid walls. They're adding insulation and they are reducing the performance, but they'll tick off that EPC.
This video is about an alternative of measuring the HTC using recording thermometers like these to measure the inside and outside temperatures and combining them with the energy data from your smart meter. This is a good location to record the inside temperature as it is not near to radiators, flues, windows, external walls or incidental sources of heat such as computers or refrigerators. But it is a bit low to the solid concrete floor and close to the level of the bottom of the radiators. You may find this video a bit heavy on equations and spreadsheets. Feel free to skip through to the conclusion. There are links to each of the chapters in the description below. But I did want to explain to you the inner workings because I want you to be able to adapt the method to your energy source, energy supplier, and energy usage. A simple model of the heat energy in a building. Energy is supplied by the heating system, but then lost from the building according to the heat transfer coefficient that we are trying to measure. If the measurement is to be accurate, we need to take account of the heat energy lost due to inefficiencies, or, in the case of a heat pump, gained from outside sources. Temperatures vary continuously, but the modelling is performed separately for short intervals over which these temperatures can be approximated as constant. The raw data is sampled at different rates. Once a minute for the temperatures, once every half hour for the smart meter. So using power or energy per second throughout simplifies the calculations. Suppose the inside temperature starts the interval at T0, ends at T1, and the outside temperature is Tx. The power of the heat loss is derived from the heat transfer coefficient, and I use the symbol B for boiler to represent the power of the heating. The change in thermal energy over the interval is the change in the inside temperature multiplied by the heat capacity of the building. It seems logical to use the symbol C for the heat capacity, but also confusing, as C is the unit of temperature. One solution is to use Kelvin instead of Celsius, which has the advantage of giving your domestic boiler the gravitas of the Large Hadron Collider. Here's another idea, not my idea, time constants. This paper considered residential buildings in North America and found that in winter the majority of time constants range from 15 to 55 hours. So what is the time constant? On a graph of building temperature against time, it's the time it would take for the inside to cool down to the outside temperature if the cooling follows the tangent of the curve, not the actual curve. Surprisingly, it doesn't matter what the inside temperature is. If the relative temperature has halved, the rate of cooling will also be halved, so the time constant still applies. Think of the building cooling down to the outside temperature. The heat capacity is the energy that has to leak out per degree C of the relative inside temperature. The HTC is power, so it is the energy that will leak out per second, so divided by the time constant, and also per degree C of the relative inside temperature. By dividing the heat capacity by the HTC and simplifying the expression, we get the time constant T in seconds. So the heat capacity is T multiplied by HTC, which we can substitute in the main equation. Rearranging the equation gives an expression for the temperature at the end of the interval, and that's a key formula used throughout the video. But how to actually crunch the numbers? I chose to use the spreadsheet program LibraOffice. Here is an example spreadsheet created using the template which is linked into the description below. Each row represents 1 minute, and the temperature and energy data has been pasted into various columns. The selected cell is where the prediction formula is used. HTC and T are variables declared in the header. You may be appalled at the idea of attempting this type of work with the spreadsheet. And you may be right, because spreadsheets are labour-intensive and error-prone. But they provide flexibility. They can be adapted for the different data formats used by different suppliers, which change from time to time. It supports regular expressions for editing, which are needed to handle the variations in the format of dates and times. And it provides tools, such as the solver, to do the final step of extracting the HTC. But you may prefer to write some custom software. Fortran, COBOL, the choice is yours. In the meantime, we'll start with a gas boiler example. Open the template that you can find in the description below, and you will see 4 example rows and a skeleton graph. To make sure that the graph expands to include all the data that you paste, you want to paste your data within those 4 rows. And here's an easy way to do that. Paste the data just below the 4 lines as a trial, and then select all the rows from the middle of the 4 lines right to the bottom of the data you have just pasted. Then insert rows above to create enough space to paste your data again for real. But before doing that, many of the cells are just formula which need to be copied throughout the spreadsheet. So copy the top row and paste it on all active rows so that you don't have to do it piecemeal later. Then paste the outside temperatures and then the inside temperatures, aligning them by time. Paste the smart meter data, date, time, electricity and gas. Set the efficiency of the boiler, assumed to be the only gas appliance. Later in the video, I will explain how I measured the 58%, the efficiency of my gas boiler. I won't paste the solar power data as this is optional, as I will explain later in the video. I noticed that a column called Date Check has lots of cells highlighted in red indicating errors. I suspect that this is caused by a well-known peculiarity of LibraOffice. If we look at cells in these time and date columns, the cells appear to contain a leading quote, but it is not a real character, it's an indicator. There's lots to read about this on the internet, and what's normally recommended is that you use regular expressions to do a replace that has the side effect of clearing the indicator. And the replace doesn't have to do anything. Replace dot star by ampersand, which means replace any character 0 or more times with the same thing. I don't set the option replace in selection only, so it replaces all cells in the spreadsheet, which may take a long time because it replaces everything, which may be anything and includes nothing, with the same thing, which does nothing but fixes everything. So the spreadsheet is now complete, and we can have a look at the graph. And it looks a bit of a mess. That's because of the trial pasting of the temperature data at the end of the spreadsheet. So we need to go and clear that up. The graph now looks a lot more sensible, but the data is only usable when the solar power is not operating. I'll explain later in the video why that is. But for the moment, we want to crop the graph to show only the usable data, and also set that as the region over which the prediction is optimized by setting start minute and end minute. And then we can invoke the solver to minimize the RMS error between the prediction and the inside temperature by varying HTC and T. We have a result. HTC is 238 watts per degree C. It may look a bit too good to be true. To prove to you that the prediction is genuine, I will look up the value of the inside temperature at start minute, which is 13.7 degrees C, and set the whole column to that value. The prediction is unchanged because once initialized, it depends only on the outside temperature, the heating power, and the values of HTC and T. There is something else about the graph that doesn't look quite right. The internal temperature appears to follow an exponential curve during the cooling phase, as though it was going to level out at around 11 degrees C, but the prediction heads down in an almost straight line. I suspected that this was due to the outside temperature being measured inside the garden shed. This graph from a later test, with thermometers inside the shed and also in a coffee can outside, shows the temperature readings being smoothed and delayed. Indeed, adding a simple moving average to the can temperatures gives a trace very similar to the shed trace. Alternatively, the standard formula that we have used to predict the inside house temperature can be used to predict the inside shed temperature. As the shed isn't heated, B is 0 and HTC isn't needed. The formula is reversible, which means the outside temperature can be predicted from the shed temperature. The prediction is very noisy and chaotic because the shed temperature only changes infrequently by a fixed step size of 0.1 degrees C. This animation shows the effect of adding a variable amount of simple moving average. Too much and detail is lost, but there is an optimal amount where the true external temperature can be predicted from the shed internal temperature with remarkable precision, which seemed to me to be similar to being able to sharpen up a photo that has been taken out of focus. After this success, I was hopeful that I could improve the prediction of the gas boiler test. But it turned out that the effect, though observable, was minimal. So unfortunately, I have no explanation as to why the prediction does not match the internal temperature during cooling. The measurement depends on knowing the efficiency of the gas boiler. As shown on the British Gas website, it is often assumed that modern condensing boilers are 90% efficient and old ones 70%, or perhaps 60%. This is how I measured the efficiency of my gas boiler. The idea was to set it up to heat the hot water tank only, not room heating, so that the energy received could be measured. The energy used was found from the smart meter, while the energy received was directly related to the temperature of the tank. To measure this, some of the insulation was cut away and the thermometer glued on with thermal paste. I can't recommend that you actually do this, and I would not have done this if I had not known that the system would shortly be replaced by a heat pump. I videoed the thermometer along with a clock so as to be able to match up the temperature data with the smart meter data. All the radiators were turned off to prevent them thermosiphoning, and the cooker and boiler were labelled to prevent accidents destroying the pump or the results being messed up. The boiler was switched on for hot water only, which means the pump didn't run. The energy required to heat the tank by 1 degree C was found by multiplying the volume of the tank, the density and specific heat capacity of water, and a graph drawn of energy received against energy supplied. The heavy cast iron boiler, which must itself contain a lot of water, used a significant amount of energy to heat up, so only the part of the graph after the water tank started to heat was used to extract the trend line. The efficiency was found to be an appalling 58%, but it has to be recognised that as the smart meter only records every half hour, the conclusion is based on very few data points. The boiler is long gone, and the heating is now right up to date with a heat pump. This shouldn't have changed the HTC, and it will provide a valuable check on the methodology. But measuring the HTC is more difficult with a heat pump because it is connected to the same smart meter as the other appliances, so the spreadsheet can't take into account the extra energy that it pulls in from the outside air. The heat pump does report how much energy it uses, but that would require manual reading. So I got a separate logging power meter. Fortunately, the consumer unit has separate live and neutral wires, as connecting the meter requires one of these Rogalski coils to be looped around just one of the conductors. I also need the COP, or coefficient of performance of the heat pump. This involves writing down the energy used and the heat produced around once a day throughout the test and plotting a trend line. LibraOffice provides an equation for the trend line, and the COP is one of the coefficients. As it's the middle of January, the COP is a bit meh at 3.78, down from its long-term average of around 4. The prediction was very poor, with several peaks for which there is no corresponding increase in the inside temperature. This was found to be due to the programmed water heating at 4 a.m. I attempted to adjust for this by data cleaning, but it was a bit hokey as I was not sure whether the heat in the water heats the house as the hot water tank gradually cools down, or is lost by the hot water going down the plug hole. In any case, after data cleaning there was little improvement. There were many peaks in the inside temperature which were not matched by the prediction. I was very depressed about the project at this point. But then I added the solar power to the graph, and clearly the peaks correspond to solar activity. Forcing the prediction to the inside temperature whenever the solar power was active, made the prediction work far better. I must stress that the solar power system is not the problem. It is the solar radiation heating up the house that messes with the results. It is equally valid to limit measuring the HTC to between sunset and sunrise. Cue the Dracula metaphor. He knows when to measure the HTC.
So how do we know it's real? Like, how do we know it's accurate?
In this animation, the HTC can be varied to give a feel for confidence in the results. To make it a bit clearer, I will mask out the periods that are ignored due to the solar activity. The time constant needs to be set to something, so as shown on this inset graph, for several values of HTC, I have used the solver to adjust t to minimize the RMS error, and then fitted a curve to them. As HTC is varied, t gets the value from this curve. The RMS error does have a minima, but does not rise steeply as HTC moves away from it. So can we be sure that it is an accurate value for HTC? The data covers 5 days, actually mainly nighttime periods. Days 4 and 5 look close with HTC at 240, but days 1 and 3 improve as HTC increases to 260. Reducing HTC towards 220 produces a possible improvement on day 2. The extremes of 200 and 300 can be ruled out, and it looks to me that the HTC is in the range 220 to 260. How long must these tests be run for? And how much heating and cooling is required? Here's an example. This test is active for the period highlighted in yellow, during which the inside temperature increases at a fairly steady rate, and is then ignored because the solar power becomes active. The graph is animated to show HTC cycling up and down. Even though there is almost 10 hours of usable data, HTC can't be determined because the RMS error only varies minutely and randomly. For any HTC, there is a value of t, as shown by the yellow curve in the inset graph, that will make the prediction match closely. To find out the actual values, some falling temperatures need to be included, so that the RMS error starts to show a clear minima, and HTC can be determined with increasing certainty. This was a single test with real measured data. It is quite enlightening to run some simulations as well, because they are more controllable and cover far more ground. Each frame in the following animation is equivalent to a whole practical test with many hours of data. Heat pumps are most efficient if the inside temperature only varies to a setback temperature by 2 or 3 degrees. Here is a typical scenario, with the temperatures and energy usage varying only gradually over 16 hours. Can the HTC still be measured? In theory, the HTC is determined correctly at 250 watts per degree C, but the RMS error does not vary much with HTC. If random noise is added to the power and outside temperature curves, then the measurement of HTC becomes increasingly erratic. A single practical test will yield a very unreliable result. With the model, I can gradually modify the outside temperature curve to both rise and fall, and as it does, HTC is established increasingly clearly, and can be measured even if the heating is keeping the inside temperature steady. It's not unrepresentative of the actual tests, in which the outside temperature varied widely and randomly. It is difficult to know how much noise in the model is equivalent to a practical test, but I will finish this section by demonstrating that as the noise is reduced to 0, HTC is determined exactly. Of the 6 results from when the heating was provided by the gas boiler, I disregarded 3 outliers which resulted from bad placement of the inside thermometer. I was delighted that the results with the heat pump were distributed about a similar mean because the boiler efficiency and the COP of the heat pump were measured in very different ways. 2 extra outlying results occurred when I had some redecorating done and the curtains were taken down for cleaning. The HTC was increased significantly, showing the value of even simple forms of insulation. Overall, the results I obtained, omitting those for which there was a known issue, was that the HTC for my house is 236 watts per degree C, plus or minus 13%. That's a long way short of the 80 watts per degree C achieved for the flats in Fylingdale Court, but still well within the capabilities of my 8 kilowatt heat pump.
And what's the historical significance?
It's the high-octane heritage of the 4-minute warning. The golf ball-shaped structures housed radar installations that could detect an inbound threat thousands of miles out and give us the earliest indication of the onset of doom. They now surround these new flats with masses of insulation.
I think there are times when you can just have a little too much of a good thing.